Okay, so this lecture kind of marks a transition point where instead of sort of looking at building combinational logic, which were A, simple, and B, kind of essentially from scratch, to one where we are going to take a bit more of an engineering approach where we say that, look, let's design some reasonably complicated subsystems, widgets, put our effort into designing them, understanding them, and then we can make even more complicated things just from that. So essentially, another way of saying is that we raise the abstraction of what we think of as a component. Okay, so thus far our components were NAND gates and NOTs and stuff like that, to now where we are going to look at bigger things. And indeed, in almost every discipline of engineering and science, that's how we kind of deal with complexity. We kind of create some more complicated subsystems and then use them to build even more. And in fact, one generation's system is probably the next generation's component. Okay, I mean, not too long ago, designing processors and microcontrollers used to be the thing that we would teach students and all, and we still do to some extent, but increasingly now we talk about creating even more complicated things where we almost take those processors and all just as components. So modular design. So combinational building blocks is what the theme out here is. So just to recap, I mean, the previous module was basically about that we kind of showed that how to take an arbitrary function and how to arbitrary function which is intended as a combinational logic, and how to implement it. And we saw probably the biggest example we had was 5 or 6 variables perhaps. And indeed with design tools, you could go and do things which would be hundreds or maybe even thousands of inputs. Of course, manually we will not even think about doing them. But even with tools, there is sort of a disadvantage. That tools are good. They're probably better than most of the designers. But there are certain mathematical functions which have a structure underlying them. And we as humans have, or whatever, very smart humans or mathematicians have kind of worked at coming up with very optimized implementations of these, which no tools can match. Okay, because we know something about the mathematical properties and we can exploit them and come up with very efficient implementations, and partly because if we were to make them efficient, then there is a lot of money at stake, or they're just useful things. So things like, I don't know, adder, multiplier, these are functions which we use quite a bit, and therefore a lot of people put effort into designing very efficient algorithms for creating implementations of these. So what we'll see, so sort of moving from this sort of low-level design to one where we are going to say, let's look at some of these building blocks. And if you played with Logisim, on the left-hand side in the palette, they have some of these more complicated building blocks just because they have been found to be quite useful. I mean, as you can imagine, things like adders and all are used quite a bit. Another reason, of course, is that the tools were not always there. And even now, tools are not always affordable. They are indeed, these design tools run into hundreds of thousands of dollars per year licensing fee. So they are not something that for tiny jobs you are necessarily going to use. It's something which where your design task has to kind of meet certain, it has to make economic sense. So what are these building blocks and all? In some senses, these are the subsystems in terms of which we design more complicated things. So we'll see over the course kind of bunch of things. There's something called decoder, encoder. Intuitively, they would probably make some sense. I mean, decoder takes some bits which are coded and then decodes them into some other form. Encoder is the reverse. Multiplexer, again, is a term that in our to multiplex something. So it's something where which can handle multiple inputs and steer one of them to the output. Arbiter, again, with the plain English meaning, arbitrate, select a winner, basically. comparator to compare, and of course arithmetic functions and all. So there's a whole list of these functions which you might imagine that if I were to give you a task that design a system like this, then mentally you'll try to come up with an algorithm for it. Okay, I mean designing hardware is the first and foremost thing is to come up with an algorithm underlying that hardware. It's just like software design in that sense. And the primitives in terms of which we like to think about these tend to be these kind of things, or arithmetic functions or similar things. So they are our building blocks. You can think of them as the hardware analog of a well-designed subroutine library, and the interfaces to these modules are your SDKs or APIs that in case of software you are used to dealing with. So let's start with that. We'll first start with decoders and encoders. So let's look at an example of what kind of decoding and encoding tasks we do. So oftentimes we talked about in the very first lecture that how we represent information digitally, and we found that for some of the things that we saw, we could represent the same information in many different ways because they serve different they had different properties. So, and this is true even for something as simple as, like, let's say I want to represent numbers. There are many different ways I can map numbers to bits. And so let's say my task is that I have a set, and the set has n elements. These could be integers from 1 through n, or there could be n fruits or n colors or whatnot. And I want to represent them I want to represent them digitally. One of the ways you can represent these things is a so-called one-hot representation. We actually saw it earlier also. And what one-hot representation says is that if I have n things to represent, then I'm going to represent them using n bits. And what I'm going to do is that exactly one of those n bit is going to be set corresponding to which element I'm referring to. So if I have digits 0 through 9, then I have 10 elements, and maybe then I'll, in a one-hot representation, I'm going to take a 10-bit code, and then I may say the leftmost bit is 1 whenever the number is 0. The second from the left is 1 whenever the digit is 1, and so on and so forth. And the idea is that one and only one bit out of the 10 bits is going to be high. So that's called one-hot coding. In the example on the slides, we are basically trying to represent numbers from 0 through 7, so there are 8 of them, and therefore what we have out here are 8 bits, and what you would see is that exactly one of them, in each one of them, exactly one of them is high, and one of them is 1, and the rest are 0. Now, this obviously is more redundant, more wasteful representation than a more conventional representation of the same digits, which are in terms of in 3 bits of kind of the natural base 2 representation that might imagine, that one might do. And there are certain operations which are easier with this. There are certain operations which are easier with the one-hot representation. We had discussed some of these when we had originally discussed, but I'll throw it out. So what do you think might, so we are representing numbers. This is our conventional binary representation. This is the one-hot one. What operations do you think are easier with binary versus, and which are easier in one-hot? Any thoughts? When you're what? When you're comparing the order, okay, at least for humans it's easier. Yeah. Okay. What else? Think arithmetic operations, addition. What do you think would be easier? Actually, anyone knows how to add binary numbers? You do. Anyone else? How do we add decimal numbers? Multi-digit decimal numbers. How do you add them? Good. So we start from the least weight ones. There's a carry. Then in the tens place, we will have 3 numbers potentially. Again, the same story. And the carry is always going to be either 0 or 1. So we know that at any stage, we can only have a carry of at most 1 out. Okay, that's the. Same approach you can apply out here also. So let me show. We'll come at it later in the course also. But let's say I want to add, I know, 0, 1, 0, and 0, 1, 1. This is the number 2. This is the number 3. 2 plus 3 is 5. 5 can still be represented in 3 bits. So we are okay. So following your recipe, so the least significant bit is on the right hand side. So I'm going to add 0 and 1. So I get 1. There is a carry of 0 out here. So 0 plus 1 is 2, which is 1, 0. So that means I have a 0 out here, and I have a carry of 1. And then 1 plus 0 is 1, 1, 0, 1, and that's 5. Okay. So exactly analogous to doing addition on the decimal base 10 system. In fact, for any base addition, long addition rule is exactly the same. And in fact, for other operations also, subtraction and multiplication and all the analogous things, it's just that our brain gets hardwired into base 10 because that's what we are taught in kindergarten. But in some other civilizations, it could have been different. In fact, what other bases have been used in humanity historically? Anyone? Base 60. Who used to use them? Yeah, Babylonians, Mesopotamian. Yeah, okay. What other base? Any thoughts? Base 60 was obviously, which is where we get hours, minutes, and all. I mean, they kind of come from that. Base 20 was actually used by some civilizations in South America. Okay, so that's another one. Base 10, I guess, came out of, I don't know where the base 10 came out of, but the place value, I think it's between Arabs and Indian civilization. I think the combination thereof kind of resulted in the place value system. Chinese also had some variant of it. So I think multiple, historically, kind of many different things had emerged. Binary obviously really came because of the emergence of digital computers. 1930s is when, in fact, before computers, the other place where binary was being used was a telephone switching system. Okay, so that's where it really had its sort of roots, and then kind of came into computing. Anyway, with that digression, so that's the one-hot representation. Okay, decoder. So decoder is a module. What it does is, so at a conceptual level, a decoder is something which takes an encoded information and decodes it, right? So that's what it. So decoder converts. Another way of saying is a decoder converts symbols from one encoding to another. Okay, it could take something. Now, usually, when we say to decode something, we are usually saying that we are taking something which is in a more complicated form and decoding it into a simpler form, right? So we are taking encrypted information and decoding it into plain text, or so decode kind of implies going from something complicated, hard to understand, to something which is easier and simpler. But a binary to one-hot decoder is basically taking this compact representation, which we have, the 3-bit numbers in our previous slide, and converting them into a one-hot coded symbol, which we are basically saying is easier for us to kind of grasp. So a decoder is a module which takes a signal which is n bits, and it is encoded in this natural binary encoding that we have for numbers, and then it outputs the one-hot coded version. So specifically what it does is, if input A corresponds to the decimal number I, then the ith pin on the output, the ith signal on the output is going to be 1. And the rest would be 0. So specific, now, if I have an n-bit signal on the input, then how many bits will I have in one hot coding? Up to 2 to the power n, right? I mean, that's the different number of numbers that I can represent. So at most I can have 2 to the power n signals on the output. So 2 to the power n at most on the output. Generally, in a more general case, I may have fewer. So that's why I've shown m there, and m is less than equal to 2 to the power n. If, for example, the n-bit signal was the number 2 corresponding to the number 2. So if let's say n was 3 in our example, and the 3-bit input presented was 0, 1, 0, which is 2, then B of B2 would be high on the output side. Anyone, just to remind you that this notation where we have cross /n and /m, they correspond to saying that this is an n-bit signal and an m-bit signal. Okay, m-bit and n-bit. So just a reminder. Okay, so that's just definition of a decoder. That's how we are defining it. See this symbol out here? Anyone recalls from your programming classes what that stands for? What is this less than sign? You said output. No. It is in C++, but that's not how it is being used out here. Yeah. It's a left shift. Okay, so it's basically saying I'm taking my n-bit number or whatever k-bit number and I'm shifting it left. Okay, so let's say my number was as shown 1, and if the number 1 you can think of as has a 1 in the least significant bit, and it has a whole bunch of zeros out here which we never write. So if I were to write 1 left shift by 2, that basically says shift this 1 which is in the least significant bit 2 bit positions to the left. So it would come out here, and what are we inserting out here? We are going to be inserting zeros. This particular left shift stands for that. Okay, so this is called a logical left shift, which basically shifting left we are going to insert zeros. Shifting right, if let's say I had the number 101 and I were to say 101 right shift by 1, that would correspond to 1 will fall off, the 0 will come to the 1's place, this left 1 will come out here, and then we'll feed a 0 out here. Okay, so this is called logical right shift or logical shift right. Okay, logical shift. There is another type of shift which is called arithmetic shift. We are going to see that later. This is logical shift left. Okay, so if we go out here, another way of describing our decoder function is basically saying that B represents a number which corresponds to 1 shifted left by A times. Okay, and that stands to reason. Like if you think about it, if A is 0, then B, the bits, the multi-bit signal B is going to be 0, 0, 0, 0, 0, 1. Okay, which stands to reason. If A was 1, then B0 would be 0, B1 would be 1, and B2 upwards will all be 0, which also kind of makes sense for us. And so on and so forth. So you can convince yourself that I can think of this decoder either in terms of this one-hot coding, where we are basically saying that all the output signals are 0 except the ith one, where I is the decimal number corresponding to whatever A represents. Alternatively, I can think of both A and B as binary coded numbers, and we are basically saying that the binary coded output B corresponds to 1 left shifted A times. Okay, and they are kind of equivalent. They correspond to the same mathematical function. So this actually kind of also brings out another point. How we interpret a bunch of bits depends on the context, right? I mean, the same out here, if I were to just give you this number 0, 0, 1, 0, 0 and ask you what does it represent, the answer is I don't know. You have to tell me what is the coding scheme. If I were to tell you this represents a one-hot coding scheme, then you know that this guy represents 2. But if I were to say it represents a binary coded signal, then the same bit pattern represents 4. Okay, so bits by themselves do not have any semantics and meaning to them unless I also tell you how to interpret those bits. Okay, so don't assume that anytime I have a bit pattern, it has to be kind of a binary coded number. It doesn't have to be. It just depends on the context. So anyway, same module can be described 2 different ways. So let's try to implement this function. Okay, so let's try to implement a 2 to 4 decoder, right? So I'm taking n equal to 2. I'm taking a 2-bit number, and by the time I one hot encode it on the output, I'll have 4 bits, up to 4 bits, right? So 2 bits on the input, 4 bits on the output. So the decoder is written usually like this: 2 to 4 decoder. Or more generally, it would be written as n to the power n decoder. Okay. So this is what we have, and we can write a truth table. Now the difference between systems we have seen thus far and this one is that here I have multiple output bits, but multiple output bits is no big deal. You can just think of them, in this case I have 4 output bits, you can just think of them as I have 4 1-bit systems, 4 systems with 1-bit output each. Okay, but I can draw their truth table in one go. So this, what we are going to do out here is we are going to draw a truth table which corresponds to kind of you can think of it as really 4 truth tables, okay, rolled into one. So if I look at A1, A0 to be 0, 0, then B3, B2, B1 would be 0, and B0 would be 1. Stands to reason because we just discussed if input represents the number I, then the ith signal on the output is going to be high, the rest are going to be 0. With 0, 1, what do you think will be the output? 0, 0, 1, 0, and hopefully with 1, 0, it would be 0, 1, 0, 0. With 1, 1, it would be 1, 0, 0, 0. Okay, so next few slides is that. So that's what we really have. This thing is, again, there are 4 truth tables out here. They're sharing the input side, and of course, column B3 column corresponds to one function, B2 column corresponds to another one, B1 to another one, third one, and B0 to another one. And indeed, I can implement this thing using strategies we discussed before. You can separately kind of draw now 4 Karnaugh maps, or whichever way you want to come up with. There are 4 implementation. One thing you would realize is that since I have really got 4 separate functions, the Karnaugh map approach can be quite inefficient, because if I were to do the Karnaugh map approach, I'm going to create 4 separate implementations, but maybe they could share stuff. Maybe they could share some gates and all, and that opportunity would not be there if we were to do the manual approach that I previously talked about. Unfortunately, there is no good manual approach to recommend. This is where design tools help you. They can also take care of these kind of multi-output systems very well. But with Decoder, we are going to do things by hand, because we want to come up with good implementations by hand. So this is an implementation, as you can imagine. So what we are doing out here is we are basically taking A1, A0. We are also generating inverted versions of them. So I really have now, first thing we do out here, so after inversion, we have both A0 and A0 not, and A1 and A1 not available. And if you think about it, B3, B2, B1, B0 just correspond to different, so B0 is high whenever A1 is low and A0 is low, and is 0 otherwise. So that in a way is corresponding to minterm number 0. Likewise, B1 is high only in one place. So this is basically saying B0 is M of 0, B1 is M of 1, B2 is M of 3, and B4, sorry, M of 2, and B4, I'm messing up, B3 is M of 3. Okay, and if you look at these inverters and AND gates, they're basically generating the 4 minterms, and we're just calling them that. Okay, so it's a fairly straightforward function if you kind of think about it. So again, strategy with a general decoder is we generate, we take inputs, we also generate the inverted version, and then we play with all possible combinations, because all minterms are going to appear in the output, one for each one of the possibilities. So that's our decoder implementation. Now the problem with this strategy is that you don't want to build decoders always from scratch. So what usually happens is that you may be, much like you are given when you're writing software, a library of subroutines or library of classes, and then you kind of build your software system using that. In hardware, what you might be given is a bunch of decoders, but you need a decoder of a different size. Okay, so let's say I give you 2 to 4 decoder, 3 to 8 decoder, and now your task is to make 4 to 16 decoder. Well, but there is no 4 to 16 in the library. So one thing you can do is you can say, hey, tough luck, I don't have 4 to 16, let me start from scratch. I can kind of do it this way, but that's not very desirable. So we would like to be able to build bigger decoders from the decoders which I already have. Okay. Now, one strategy is if I give you a 4 to 16, let's say I gave you a 5 to 16 decoder, and you don't have a 5 to 32 decoder, and you don't have a 4 to 16 decoder, I can always use the 5 to 16 as a 5 to 32 as a 4 to 16. How would you do that? So let's say I give you a decoder which goes from 5 bits to 32 bits, but I actually needed a 4 to 16. Okay. No, I'm giving you a hardware widget. Okay, so now I gave you a physical box. I'm saying that, look, it has 5 inputs, it has 32 outputs, it's a 5 to 32 decoder, but you only needed a 4 to 16. What would you do? It's not a deep question, guys. So, huh? What would ignoring mean? I mean, I have to tie inputs to something, right? So what would you do?
I mean, if you set it to 1 or 0, that will always. Right?
What would you set to 1 or 0 always? Huh? Someone said 0. Yeah. So what did you have in mind? Where do you want to put zeros? Right. So which input do I not need? So I have 5 wires coming in, A0 through A4, but I only needed 4-bit numbers. So no, you're thinking too much. Okay, if I gave you 5 bits and I only want to represent 4-bit numbers, set the upper most significant bit to 0. Right? Nothing deeper than that. So you just set A4, tie A4 to 0, and A3, A2, A1, A0 become your 4-bit thing. Okay. So I can always do that. So again, I had a library where I gave you 2 to 4, 3 to 8, 5 to 32, but I forgot to give you 4 to 16, and hey, I needed 4 to 16. So one strategy is take 5 to 32, tie the most significant input bit to 0, and I'm in play. What's the problem? I mean, there's no functional problem, but why is this not a good way to go?
You're wasting.
Yeah, wasting, right? I mean, 5 to 32 is going to have a lot more gates. It's probably going to cost more money, burn more power, have more silicon area, blah, blah, blah. So that's not a good strategy. So what may be a better strategy is, maybe since I had 3 to 8, can I make 4 to 16 out of that? So this is a long drawn motivation to, can I build large decoders from several small decoders? So let's see how we can do that. So let's say I want to build a 6 to 64 decoder from 2 to 4 decoders. Okay, so I have a supply of 2 to 4 decoders, and I want to make a 6 to 64 decoder out of that. Okay, so each 2 to 4 decoder decodes 2 bits, right? So what I can do is I can take the lower 2 bits of, so my input A has 6 bits. I can take the lower 2 bits of A, decode it, let's call it X, and since it will decode it to 4 bits, so X0 colon, X3 colon 0. I can take the next 2 bits of A, A3 colon 2, and let's call it, they decode to Y3 colon 0. And I take the uppermost 2 bits of A5 colon 4, and call it Z3 colon 0. Okay, so just 3 2 to 4 decoders. I take these, I take pairs of neighboring bits and decode and decode them. So I could do this, right? So what is happening is that I can create these 3 truth tables where each one of these corresponds to a 2 to 4 decoder. It's just that it's operating on different 2 bits out of the 6-bit A. So the rightmost one is operating on A0, A1, the middle one on A2, A3, and the final one on A4, A4, A5. But remember, what I want to create is something which takes 6 bits of A and produces 64 bits on the output. What I have though are pairs of A's which have been mapped into these 4-bit sequences. Now, so question then becomes, is there a strategy I can generate those 64 bits out of what these intermediate things I have, X, Y, and Z, which are 4-bit each? So let's see how to do that. So what we do is, so if you think about it, I have 4 possibilities from this decoder, I have 4 from middle decoder, and 4 from the rightmost decoder. And my 64 possibilities at the output correspond to different combinations of these. So if you think of when Z0 is high, and Y0 is high, and X0 is high, if that is the situation, then which one of my 64 B's should be high at the output? Right? So Z0 being high means A4 and A5 was 0. Y0 being high means A2 and A3 was 0. And X0 being high means A0 and A1 are 0. So my input number was 0, 0, 0, 0, 0, 0. So B0 should be high at the output. So B0 being high means B0 is high whenever Z0 is high and Y0 is high and X0 is high. Stands to reason? Okay. When do you think would B1 be high? Okay. Z1 is high, and so Z1 is high, and sorry, Z0 is high, Y0 is high, and X1 is high. Right? So B0 equal to 1 is the same as saying Z0 and Y0 and X0. Likewise, B1 equal to 1 is the same as saying Z0 and Y0 and X1, and so on and so forth. So I'm always going to pick one out of each one of these decoders and combine them. How many possibilities are there? 4 times 4 times 4, 64. They kind of match up. Okay. This general equation out here is stating the same thing. It's basically saying that if BI is high whenever, and then what I do is I select the right thing out of X, the right out of Y, and the right out of, so this is kind of a funky notation out here. It's basically saying that I take the number I think of that now in my binary notation. So I look at the lower 2 bits of I, whatever number they form, it would be a 2-bit number, so it will go from 0 to 3. I take that particular X, and likewise I look at bits 2 and 3 of I, and I pick that particular Y, and likewise for Z. So let's see if it works out. So if I'm looking at the number B0, so in case of B0, I1 colon 0 is 0, 0. So I'm going to pick X of 0. I3 colon 2 is also 0. So Y, I will be picking Y of 0. And finally, I5 colon 4 is also 0. So I will be picking Z of 0. Let's try another number. Let's say I want to look at when is, I don't know. Let's look at B of 32. Let's say I want to look at that. So 32 in binary is, if I look at 32, in binary it's going to be 0, sorry, yeah, it would be 1 0 0 0 0 0. Okay, that's what it would be in binary. So looking at this, I'm going to look at these pairs. So it's basically saying this is 0 0, so I'm going to pick x0. The middle one is 0 0, so I'm going to pick y of 0, and the upper one is 1 0, so I'm going to pick z of 2. So that means b of 32 can be implemented as z of 2 and y of 0 and x of 0. And I can play the same game with any, for each one of my 64 outputs, I can form such things. So I can, again, so my stage 1, I use these low-level decoders, and then I combine their outputs in all possible 64 ways. Okay, so I'll need, obviously, a supply of AND gates to pull this thing off, but that would be kind of the strategy. So this is what is happening out here. You see that I took my 6-bit input, I fed it into 2 to 4 decoder. Each decoder gave me 4 bits, and in each one of these decoders, each one of these 3 2 to 4 decoders, at any point in time, one and only one of the output would be high because a decoder does one hot coding. And then I create all 64 possible different combinations where I pick one signal from each decoder and I combine them, and that will give me my 64 signals on the output. So I can, so in this case, I need 3 2 to 4 decoder and 64 AND gates. Okay. Same strategy can be applied for obviously bigger things. So like now, let's say I gave you 6 to 64, and I want to create 7 to 128 decoder. So let's say that's what I want to do. So I'm giving you 6 to 64 given, and I want to create 7 to 128 need. So the strategy out here now would be, I'm going to, so I have a 7-bit signal. I can take the lower 6 bits and feed it into the 6 into 64 decoder, and then I have 1 bit left over, and I can now form every possible combination of this 1 bit with the 64 signals I have. So I'm going to walk you through some example out here, but let's take an easier one first. Let's say I want to create 12 is to 4096. Yeah, 10. Am I right? 10 is 1020. Yeah. So 12 is to 4096 decoder. So what I can do is I can take 2 of these 6 is to 64 decoder and then form every possible 64 square combination out of that. Okay, so that's kind of the general strategy. Question?
That means that you get 4096
outputs. Yeah. It would be lunacy. You'll never do it, but I just wanted to present that as an example. Usually, I mean, you're never going to go, I mean, by the time, when you're dealing with decoders, maybe 6, 7 inputs is probably where you're going to max out. Yeah. Okay. So I can make bigger decoders out of smaller decoders. And we'll sort of practice some more about this. But let's talk about what are the advantages of dividing this larger decoder in terms of smaller decoder. Let's think about, so one of the motivation, of course, like I said, was that, hey, I may not have in my library this larger decoder. I may just have a supply of smaller decoders and I want to build it up. But there are also other possibilities, okay? So let's look at how many gates may be needed. So if I do, 6:64 decoder, then that's and I just want to build that up using from scratch, using this kind of strategy, this kind of approach where I basically do the truth table and kind of form all those minterms. So if I have 6 inputs, I have 2 to the power 6 rows in my truth table, and I have to cover each minterm once. So if you count the number of gates that you would need, I would need 64 6-input AND gates, because I would need to form each of the minterms. I have 64 minterms, and so for each one of them, I'm going to need an AND gate. And each one of those AND gates is going to have 6 inputs, because it will have each one of the inputs going into each AND gate, either directly or in a complemented form. So I would need this, plus actually I will also need 6 NOT gates. Right? That's what we would need to realize a 6:64 decoder just using AND gates and inverters, just like that. On the other hand,
why is the 6 not good?
Because remember, to form minterms, I also need the negated version. So if you go back to the analogy with the 2 to 4 one out here, see how I needed the 2 inverters, right? That's because I have to form every possible combination, every possible minterm out of it, right? So, okay. So I will also need those NOT gates. If on the other hand, I want to make this 6:64 using 2 to 4 decoders. So now remember, 2 to 4 decoders needed, these 2 to 4 decoders, as we saw previously, they needed 4 AND gates, 4 and 2, because they need 2 input AND gates, plus 2 NOT gates. And I would need 3 of these, because I need 3 2 to 4 decoders. But then I also need additional gates, which so this is why you get this 12 input AND gates, okay? But then I also need 64 3 input AND gates, because I need to combine the outputs of these decoders, one from each decoder, as we just saw in the slide, this one. So I also need 64 AND gates out here, 64 3 input AND gates. So you combine all of them, I get 64 3 input. Now I mentioned, and I think it was a previous lecture, that the cost of a gate is proportional to number of inputs in it. So you can count the total number of inputs these gates have. So in the first strategy, I have 384 input lines. In the second strategy, I have 24 plus 192. We are ignoring knots, that tiny part out here. But as you can clearly see, that this second strategy is actually cheaper in terms of the overall cost than the first strategy. So it's more efficient, more. So even though number of gates here is more, 64 plus 12, but these are smaller gates, 2 input and 3 input. Here I have 64 gates, but they are monster, 66 input each. Okay, so the first strategy ends up having a bigger area, more cost. So second strategy is more efficient. So where am I losing? I mean, in engineering, is always a trade-off. You win something, you lose something. What am I losing?
Here, a little lower.
Yeah, I mean, this guy is lower area, but then where is it losing out?
Delay.
Delay, yeah, delay. Why delay? Anyone? It has to go through more AND gates, because first has to go through the AND gates in the 2 to 4 decoder, and then it has to go a second layer of AND gates. Whereas here, I just had to go through a single AND gate. Okay. So it loses out on the delay in this case. So let me just write it. But whereas the first strategy, 664 direct, just one level. So the delay of second strategy could be worse than the first strategy. So now, of course, I'm making an unstated assumption, that is that a 2-input AND gate followed by a 3-input AND gate is slower than a single 6-input AND gate. Need not be true. It's kind of a complicated situation, generally speaking. But one thing to also kind of that the reality of modern technology is that gates, the delay of gates is only a tiny part of the overall delay. What other thing causes delay in a system, in an electrical system? So besides gates, what else do we have? Sensors. No, no sensors. There are no sensors out here, right? So I have gates, but what else do we have? Wires. We have to wire them up, right? And wires have delays too. Okay. And the delays, why do wires have delay? Hmm? Yeah, I mean, so firstly, there is a speed of light limitation. Nothing can travel faster than speed of light, but that's not really the main delay. I mean, you're talking about chips. The delays, the speed of light part is minuscule. Okay, so go back to your physics, or if you're already doing any of the E classes, resistors, time, capacitor, moment. Wires have resistance. Wires have capacitance. Anytime you have R and C, they come together and cause RC delay. If you've done AP Physics, you should have seen it. Essentially, if you look at the voltages, they kind of rise slowly because of this RC time constant. So, moment I have a wire, signal takes time to travel, and the delays of these wires dominate. Okay, so that was again a digression, but the point is, it's not quite necessarily the case that. So it may be that 6-input AND gate, the gate delay may actually be smaller than the sum of the delay of 2-input AND gate plus 3 AND gate, but by the time you take wires and all into account, you're probably, this is most likely slower. Okay, so so decoders, from small decoders, I can make big decoders, and again, Paul and Salma are going to sort of try out some examples there, and we'll also have something in the next homework. But what's the value of having decoder? Of course, they do this binary coded numbers to one-hot coded numbers, but so what? I mean, if you think about the set of functions you write and all, it's not like you go around looking for doing binary to one-hot decoding. That's not item that we encounter a whole lot. The reason decoders are useful is that I can actually implement arbitrary logic functions with decoders. Okay, the homework that I've handed out has this thing about universal gates. You can think of this thing as sort of a universal module. It can implement arbitrary logic function, of course, with certain number of inputs only. So in particular, if I have in particular, if I have a k input decoder, then it can implement any, I can use it to implement any k input function. And the strategy is the following, that if I have a 3:8 decoder, then it takes 3 inputs and it produces 8 outputs. Output number 0 being high, what does it mean in terms of minterm? So when is output number 0 going to be high? When the inputs are, in this particular case, so what would be the value of n2:0 for output for B0 to be high? So when is B0 high in terms of n2:0? 0, 0, 0. What does it mean for our minterm? Which minterm is true? Minterm 0. What about B4? When is B4 high? B4 is high when input has the value 4, 1, 0, 0, which means M4 is true. Okay, so I have 8 outputs. They actually correspond to the 8 different minterms. Output number I is high if minterm number I is true. And now if you think of a function, we've talked about a function is nothing but a ORing of some of the minterms, right? I mean, I can take a function and say this function is equal to minterm 0 ORed with minterm 3. Another function is minterm 1 ORed with minterm 2 ORed with minterm 5, and so on and so forth. For each minterm, we can say whether it occurs in that function or not. So all I need to generate my function is to OR the relevant outputs of my decoder. So if you want to implement a k input function, I give you a k input decoder, you take that decoder and then just OR the relevant outputs of that decoder. So if you go back to our good old one OR prime function, so 1, 2, 3, 5, 7 in a 3-bit number, we are just ORing them out here. If we were to say is even, then we are going to take B0, B2, 4, and 6, and so on and so forth. So decoders are great because I can just give you a supply of decoders, and you can implement arbitrary logic functions. You still need an OR gate, but that's a minor point. And since we also told you how to build larger decoders from smaller decoders, so you can have that strategy and then kind of build more complicated functions with that. So decoders are powerful in this regard, that you don't have to think about Carnot maps and stuff like that. I mean, you just basically pick up the right size decoder and work with it. Okay, what's the disadvantage? And this works great, right? In one go, I told you, forget about Carnot maps and all, just use decoders. So what am I losing? It's always in engineering, always we lose something, yeah.
Maybe outputs?
What do you mean by maybe outputs? What were?
Well, maybe it's just this type of decoder, but if I need an output full of ones,
No, I can create any function. I just need to combine the right set of outputs. Right? So, but what aspect of my overall system am I losing on? Is it costlier? Is it slower? Is it whatever? So wasteful? Is it? Look at this example. Is there stuff that I'm not using? Right? Is there part of this logic which I could have easily eliminated? How many outputs does my decoder have here? 8. How many of them am I using for my OR gate? 5. What's happening to the other 3? They're just hanging loose, right? So all the stuff behind that output, those 3 outputs, is being wasted, right? So decoders are general purpose, but they always come in this k input, 2 to the power k output. But I don't necessarily need all the 2 to the power k minterms in any given function. So a lot of them are wasted. So that's a disadvantage. On the other hand, it also has advantages. Let's say in the same module, I needed 2 output, is prime and is even. Then I can share this part of the decoder, and is even can just be tagged along as a second OR gate, right? So for multi-output functions, I can easily create, I can share the decoder part and then just have different OR gates and output, or OR gates which are combining different minterms. So it has benefits, it has negatives. I guess it's pretty wasteful if I have a function which needed very few minterms, but it is pretty useful if my outputs end up making use of most of the minterms. That's one way of kind of looking at it. So it's a very powerful module, but needs to be used carefully. But you'll find it in libraries, and again, if you would like to go and sort of just open Logisim, and you'll see there's a decoder module, and that decoder module you can set how many inputs it has and a bunch of other properties of that decoder, and then you can use it. So it can be used. I mean, even It's very commonly found in libraries. Okay. So that was decoder. And there are many other types of decoder, but the one I described is the most, when we say decoder in digital logic, this is what it specifically means, although in more general computer science, electrical engineering usage, there are a whole bunch of other kind of decoders also. Okay, opposite of decoder is encoder. We go in the reverse direction. Specifically in our case, I have input now which is one hot coded and the output is binary coded. Okay, so we just want to go in the reverse direction. So 422 encoder, I have four inputs, A3, A2, A1, A0, and I have two outputs, B1 and B0. And if you look at, so input A is one hot coded. So if A0 is 1 and the other three are low zeros, then B1 and B0 are both 0 because the number 0. If the A3, if A is 0, 0, 1, 0, then output is 0, 1. If A is 0, 1, 0, 0, output is 1, 0, and finally 1, 0, 0, 0, output is 1, 1. Do you see something odd about this truth table? I have 4 inputs. How many rows should I have? 16. What happened to the other 12 rows? Don't care. Remember, don't care. We don't care. Okay, why don't we care? Because they are? What do you mean by they are one hot? So let's say we consider the input pattern 0, 0, 1, 1. That can never occur. It's not a valid one hot coded signal, right? So we started that our input has to be one hot coded, right? So the remaining 12 rows should never really occur. Okay, if they occur, there is some problem. Okay, now sometimes these encoders make some. It's very common to say that if all inputs are 0, then there is some special thing to be done at the output. Okay, sometimes you will see these kind of encoders, but conceptually speaking, at least what we want to say is that since input is one hot coded, then the remaining 12 rows really should never occur, and therefore they truly are don't cares. Okay, because if some input pattern can never occur, then we can safely say that I don't care about the output there. You have a question? No. Okay.
Wait, so one hot coded, what does one hot coded mean?
One hot coded.
Oh, so it's just one of them.
One and only one, right?
Okay.
So that's the important part. So we can never have 2 or 3, 1 or whatever. In this example, just exactly one of these bits should be high. Okay. So the remaining 12 values are not valid one hot codes, and therefore they cannot occur, and therefore the output for those cases is don't care. Okay. So looking at this, we can write the equations for these relatively easily. If you look at B0, B0 is high when A1 is high and A3 is high. So that's what you see out here, or A3 is high. So B0 is A3 or A1. And likewise, B1 is high when A2 is high or A3 is high. So B1 is A3 or A2. Okay, so these are basically, both of them are just OR gates. So a 4 to 2 encoder is nothing but a couple of OR gates. So pretty trivial. Okay, just like we talked about building bigger decoders from smaller decoders, the same thing out here also. We want to build bigger encoders from smaller encoders. And this is where a little bit of variance from this picture that I had in the previous slide one has to go into. And the reason is the following, so we'll shortly see the reason. And one thing you would immediately notice is that I have 2 outputs out of these encoders, and I'll explain why we have 2 outputs. Okay, so let's say I want to create 16:4 encoder. So it takes 16-bit one hot coded signal, and my output is going to be 4 bits because I have 16 possible values, and I'm giving you a supply of 4:2 encoders, and I want to create, specifically I've given you 5 of them out here, okay, but I want to create these. So natural thing is, I again am going to take my input. I have 16 inputs, and since you gave me 4:2 encoders, so I'm going to take groups of 4 input bits and feed them into different encoders. So I'm going to take the lower 4 bits and feed them. So lower 4 bits are going out here, middle 4 bits out here, whatever, bits 4 through 7, 8 through 11 out here, and 12 through 15 out here. Now, remember, we said that the encoders must see a 1-hot coded input. And my 16-bit input is 1-hot coded. Do you think each one of these 4 encoders will see a 1-hot coded input?
No.
Why not? Yeah, the answer is no, but why not?
Some of them are 1, 1.
Some of them are
Some
1,
of them
1.
are 1, 1, 0, 0.
No, there will never be 1, 1. Yeah, so 3 of them will be all zeros, right? Because my 16-bit number had exactly 1 bit as 1, right? That's why it's a 1-hot coded number, right? So that 1 bit, that high bit will occur in one of these 4 encoders, right? So let's say A10 was high, okay? So then if A10 was high, then this encoder is going to see a 1 in its bit number, its 3rd bit, but the top encoder and the bottom 2 encoders are going to see all zeros, okay? So I need to handle this case somehow now. And that is why we have this extra output out here, which basically says, hey, I'm seeing an all zero pattern. Okay, so the red signal that you are seeing out of every encoder is basically saying that, look, actually it's the other way around. The red signal basically says that I'm seeing a valid 1-hot code. Okay, so what will happen is that 3 of these encoders are always going to output 0 on the red line, and one of them will output a 1, and that the one which will output a 1 would be the one saying, hey, I'm seeing a valid signal. Okay, because remember, otherwise what will happen, let's say again, taking my example, that A10 was high, then the upper encoder is seeing 0, 0, 0, 0, and depending upon my implementation, the 2-bit blue line can have any value. Remember, that was don't care. So I need to output out here saying that is the output on blue line valid or not. So red line is basically saying if red is high, then the output on blue line makes sense. If red is low, output on the 2-bit blue line is bogus. Okay. So now what is happening is that we are feeding my 16-bit 1-hot coded divided into these chunks of 4 bits to the 4 encoders. Exactly one of these encoder is going to have a valid output. So what I now do is I take these red lines of the I take the red lines of the 4 encoders. Exactly one of them would be high, the remaining 3 would be 0. That in itself is now a 1-hot code. And I use another 4:2 encoder to get a 2-bit number. So let's take an example. If A10 was high, so let's say A10 was high, and the rest were 0. Okay, so then I'm seeing 0, 0, 0, 0 out here. I'm seeing 0, 1, 0, 0 out here. I'm seeing 0, 0, 0, 0 out here. I'm seeing 0, 0, 0, 0 out here. So this red line is going to say 0. This red line is going to say 1. This red line is going to say 0. This red line is going to say 0, right? Because only the second from the top encoder is seeing a valid 1. So I'm feeding it into 4:2 encoder. And so what would be the output out here? Anyone?
0.
What would be B3? What would be B2? So it's a one-hot code. What number am I seeing here in terms of one-hot code? So it says 0100. So it's the number 0, 1, 2, 3. It's the number 2, right? So it's going to see 1 and it's going to see 0 out here. Okay. And if you think about it, that kind of makes sense, because if A10 was high, so I am trying to represent the number 10 on the output, and I have 4 bits. Sorry, I have 4 bits at the output. So 10 in 4 bits is 1, 0, 1, 0, right? So that's what we want. So the upper 2 bits basically indicate which of the 4 encoders was seeing the high bit, right? If the bits were from 12 to 15, then the output should say 1, 1, and that makes sense because the number 15 is 1, 1, 1, 1. The number 12 is 1, 1, 0, 0. Okay, and likewise A8 through 11 basically says upper 2 bits of my output are 1, 0. A7 to 4, if my one hot code appeared out there, that means the upper 2 bits are what? So let's say A6 was high. What should be my output? A6 high means one hot code. What's the number in one hot code? 1100. Is that correct? So again, A6 high means what's the number? 6.
Yeah.
So
0, 0 is 1.
no, 0011 is the number 3.
Sorry.
0110. Okay, the number 6, right? If A4 is high, what should be the output? 0100, right? So if you think about it, if A4, A5, A6, or A7, if one of these is high, then my upper 2 bits of the output should be 01, right? And then finally, if A0 through A3, one of them is high, then the upper 2 bits of my output is 00. So which one of these 4 encoder sees the 1 dictates what my upper 2 bits are on the output. It's either 00 or 01 or 10 or 11, and that I am deciding using this encoder. Lower 2 bits are going to be decided by these blue lines, except I need the blue line for the one which for that one which is seeing the valid code. So now the other property of this encoder is the following. So remember we said if it is seeing all 0 pattern, it outputs a 0 on the red. But additionally, what it also does is it outputs 0, 0 on the blue lines. So in our example, when A10 is to 1, these 3 blue lines are going to see 0, 0. Each one of the blue line is 2 bits. Okay. What about this guy? What do you think we'll see out here? So it's a 4 to 2 encoder. It is seeing 0, 1, 0, 0 on the output. Sorry, on the input. What do you think would be on the output of this 4 to 2 encoder? 1, 0. Excellent. Did anyone not see why we are going to get 1, 0? I mean, I have 4 lines. So it has 4 inputs, 0, 1, 2, and 3. It's input number 2, which is high, and therefore output would be 1, 0. Okay. And what I need to do is, in the face of this situation, I have 3 of them are outputting 0, 0, and 1 of them is outputting 1, 0. I want this 1, 0 to appear on the output. I want 1, 0 to come out here, because that's what makes sense also, if you see about it. That would mean my output is 1, 0, 1, 0, which is number 10. Okay. Now, this funky notation out here, which actually I think Logisim also uses, is see how I have an OR gate, but on the output I have a 2-bit signal, and on each one of the input I also have a 2-bit signal. Okay, because each one of the blue line is 2 bits, and this output is also 2-bit. This is a stylized way of saying that what I really have is I have 2 OR gates. One which is handling the lower bits of the blue lines and outputting B0, and the other which is taking the upper bits of each blue line and ORing it and outputting B1. So let me create a blank page and kind of just make sure that we get that out. So let's say I had this situation. And I also want to do okay, and in general I may have n of these, right? One operating on bit number 0, bit number 1, bit number 2. Instead of drawing so many things, we write it like this. Okay, so same as the bottom one. So it's just notational, okay? And again, plain Logisim, you are going to see kind of the same thing. You can have n-bit OR gates. What they're really saying is I have n OR gates in parallel, okay, each operating on a different bit number. Saves a lot of painful writing. In fact, Logisim also has the ability to take a multi-bit signal and extract some bits out of it and things like that. Paul, maybe you can go over this thing. Salman, you can go over that, how to deal with multi-bit signals in Logisim on the discussion. Okay. Okay. Yeah. They also have these extract like things where you can merge multiple signals into one and vice versa. That might be a good thing to expose to everyone. Okay. Yeah, play with Logisim. I thoroughly encourage it because it also shows you a lot of conventions which are used in drawing these kind of circuits. So back to our story out here. So what this really is it's really 2 OR gates out here. With 4 inputs each. Okay, so important point to note out here. So now the reason this thing works out is if you look at any one of these OR gates, 3 of those blue lines are seeing 0, 0. And whenever I'm ORing, if I'm ORing something with 0, it has no effect, right? X or 0 is still X. So 3 of the blue lines have no effect. The blue line which potentially has 1s in it is going to appear on the output. In our particular case, I will see 1, 0 at the output, therefore, because I had a 1, 0 from this encoder out here. Okay?
So for your encoder, you actually have to fit some logic in there for it to be able to sense.
Yeah, so what happens now is that encoders are designed to be cascaded. That's the term which is used out here, so that you can make bigger encoders out of it. So the encoders that you would typically encounter in a library are not designed just like this. They have some extra logic which generates that red signal and which also makes sure that there is an entry in their truth table which basically says that if all the A's are 0, output is 0, 0. Okay, so if you think about the encoder that I am using out here, its truth table is, let me draw it for you. So let me call it sorry. So what it is doing is let's call it a valid signal. Okay. So if it is 0, 0, 0, 1, then the output is 0, 0, and the signal is valid. If input is 0, 0, 1, 0, the output is 0, 1, and we are saying output is valid. If 0, 0, 1, 0, it's going to output 1, 0, and again it will output valid. If it is 1, 0, 0, 0, then it's 1, 1, output is valid. Then we make a special case. If it is all zeros, then output is all 0, and it is not valid. Anything else? All other remaining 11 combinations, we don't care, we don't care, we don't care, because they are never going to work. Okay, so that's what this enhanced encoder that we were using in the previous slide is going to do. Okay, so just a minor little sort of enhancements to it.
So if you go back to the other slide,
Mm-hmm.
are each of those encoders have the same truth table, or that each of the four?
Each one of these four have exactly the same truth table, right? They are identical encoders. Yeah, this final one at the output is the non-enhanced encoder. It doesn't need that red line on the output, but you can still use the same one out there also if you want. So these encoders with the red lines, they are designed so that they can use to build bigger encoders. That's kind of the message out there. Okay, so encoders can be used in this way can be ganged up or cascaded to make bigger things. Why are encoders useful? Well, part of the charm of an encoder is taking more bits and shrinking them down. So oftentimes what happens is that you may have systems where there may be an array of switches. Each switch controls one bit. So like for example, let's imagine I want the user to select colors from some sort of gizmo where there are a whole bunch of colors, and we tell the user select one and exactly one color. Okay, so they press a switch. Now the easiest thing is that interface, right? One switch per color, they flip a switch. So now I have a one hot coded signal. It would be very hard to tell the user that, oh, if it is color number 5, then turn switch number 2 and switch number 0 to be on and switch number 1 to be off. Okay, binary encoding. That would be kind of a very insane user interface. So usually in user interfaces, we like to expose things directly. Okay, so we just flip the switch corresponding to your choice. And then the very first thing that you'll do in the system is to take this one hot coded signal and shrink it down into binary into a much fewer bits, so that then you can process it and all and carry fewer wires, have a more efficient system. So encoders are very common at the very front end of a system where you have large amount of information and you're just shrinking it down. So just sort of again, why do we kind of need it? And of course, the other thing is, like I said, encoder is just exactly the opposite of decoder. Okay, so let's move to the next module. So we've seen decoder, we've seen encoder. They work exactly opposite. They switch back between, they take you from one hot coded to binary encoded or whatever, regular standard binary encoded, or vice versa. Now let's look at the next one, multiplexer. So The idea behind multiplexer is the following, that oftentimes in our system, we face the following kind of situation, that I have a bunch of sources of information, and I want information from one of these sources to be sent to the output, and I want to be able to select which one. And we encounter this thing, I mean, in many systems. I mean, if you look at your stereo system, for example, at home, your sound may come from CD player and your music library on your computer, or radio station, or whatever, bunch of places, right? And then usually we are provided with some sort of a control. It basically says that which sound should feed into the speaker. Okay, and there are many other systems in our life which have this kind of characteristic, that is, there is an output, and we play with by through some control, we select which one of the input is feeding to the output, and this process this is an act of selection. Okay, and that's a very common usage of this block called multiplexer, but multiplexers can be used for other purposes also. But this is what they do. There's an analogy in software also. What in software, what kind of construct gives you this ability that output can be equal to one of possible choices? Okay, so you read the homework already. Okay, or you can have a switch statement that kind of serves a similar purpose, or a series of if then, if then, if this, otherwise this, otherwise that, right? I mean, if then, and a bunch of else's after that, right? I mean, they're all serve this purpose that we are making one out of many choices. We are selecting one condition out of many. Multiplexers kind of do essentially that role, as we shortly see. So a multiplexer block has two types of inputs and, of course, an output. So what it has is, it has a bunch of k-bit inputs. This is where our information is coming on. I have n sources, a0 through an minus 1. Each one of them is providing a k-bit information. And at the output, my output is also k-bit. So output B is also k-bit. And I want to steer one of information from one of these sources, one of these n sources, to the output. So B should be equal to either A0 or A1 or An minus 1, one of these NAs. Which one it should equal? I select using this control input. We call this the S input for select, and that is n bits. Now, with this n bit input, and it is one hot coded, I'm going to select one of the n sources. So for example, if I want B to be equal to A0, then the input S is going to be 0, 0, 0, 0, 1. If I want B to be A1, then S will be 0, 0, 0, 0, 1, 0, and so on and so forth. So this is the control input, and it is one hot coded. That's very important. And it's basically saying that if the ith bit of S is high, that means I'm selecting the ith source, and therefore B should be equal to AI. I take the k bits of AI and steer them to the corresponding bits on the output. So this is what a multiplexer does. Again, inputs are one hot coded. In Logisim, actually, they have two types of multiplexers. One where the S is one hot coded. They also, I think, have a version where S is binary coded. Okay, so if S is binary coded, then it will have log2 n bits there, log2 of n bits as opposed to n bits. Okay, but same purpose. You can you make a binary? If I want to convert this multiplexer into a multiplexer where the control was binary coded, how will you do it? I mean, did we see some module which can help us do that? Decoder, exactly. So I have encoded S, first thing decoder, then we get the one hot coded S, and then we use this multiplexer. Okay. Again, like I said, in Logisim, I think there is an option where you can select one or the other. So there are all these. Yeah, go ahead.
Is this the only type of multiplexer? Or, for example, I can have an output with lower bits and like multiplexer with functions, for example,
Multiplexer with what?
with functions.
Could you give me an example? Like what kind of function do you have in mind?
I don't know if I need to use A0 and A1 and have an output of 2 bits, but I have also an input that tells me that I have to use A0 and A1 instead of the other ones. I think that the output is not equal to an input.
Or the number of bits on the output is not the same as number of bits on the input?
Still a multiplexer, or is
No, it would be some custom function. So multiplexer takes, so the again all the multiplexer does is it takes information from one of the n sources and makes it appear on the output. So the number of bits remain unchanged and the bits are unchanged. Okay, probably the only thing you would see is that some multiplexers may be inverting. That is, the output may be the complement of the information appearing on the input. I think again Logisim lets you do that, but those are minor variations. Okay, but otherwise the information on the output is either, I mean, just comes from the inputs. Sometimes there are multiplexers which can output both the input information and the complement of the input information. So there are variations. Sometimes multiplexers may have a enable function, and if that enable input is 0, then output is all set to all zeros. Okay, so you can disable the output of a multiplexer. So there are some variations like that, but that's where it that's where it ends. So multiplexer, as you can imagine, has lots of uses. In context of a computer system, you might imagine, for example, the CPU, the processor, may get information from a bunch of different memories, different types of memories. So there might be a multiplexer at the input of the processor, and then the processor can tell the multiplexer, send me information from memory number 1, or memory bank number 2, or memory bank number n. Okay. In fact, something like analogous happens when you have, like, if you, I don't know if any of you have ever installed DIMMs in your computer, but each DIMM is a separate memory bank, and somewhere in the system there is a multiplexer which is basically taking that's each DIMM is giving you 32-bit data line, but then depending upon which memory address the program is currently accessing, the multiplexer will activate the connection to one of those memories. Okay, and then that's where you kind of fetch it from. So that's an example where we are sourcing the data from the right place, and the multiplexer helps you do that. So very important module, very many ways of implementing it with different efficiencies and whatnot, but conceptually a very powerful kind of a module that finds very lots of uses. So how can we implement it? Conceptually very simple. So remember, we said our selection signal S is one hot coded, and what we want to do is that we want to steer the signal to the right place. So conceptually what we can do is that so let's imagine my input signal, I'm looking at a 1-bit multiplexer. That is, each one of the input and the output are 1 bit each. But I have, in this particular case, I have 4 inputs. Okay, so I have 4 inputs of 1 bit each. I have the input 0, input 1, input 2, and input 3, but each one of the input is 1 bit each. I take S0 and A0 and AND it. I take A1 and S1 AND it. I take A2 and S2 AND it, A3 and S3 AND it. Okay, and then I OR it, or the output, so as seen out here. So now let's see. So remember, my S is one hot coded. So one and exactly one of the S has to be high. So let's say S1 was high. So if that's the case, so let's imagine S1 was high. So let's say this guy was 1. The others have to be 0. So this AND gate would be 0. What would be the output of this AND gate? Huh? A1, right? Because A1 ANDed with 1 is A1. So I'm going to see A1 out here. And then if you look at this OR gate, ORing with 0 has no effect, so the output would be A1. So I will see B equal to A1. Okay, so and you can obviously the same argument holds for any one of them, right? So if I have one hot coded S, then it will steer the right A to the output. Now, if I need to create a 4-bit version of this, so 4 to 1 multiplexer with 4-bit each, then what would I do? Yeah, this is a 4 to 1 multiplexer, but I'm now saying let's create a 4-bit, or let's say 8-bit. I want to create an 8-bit 4:1 multiplexer. How would you build that? So so I have 4 inputs, A0 through A3, but each one of them is 8-bit each. So how would you create such a multiplexer? Remember, in the previous slide, I had a k-bit multiplexer, right? So what I'm asking is, how would you create an 8-bit multiplexer from this? Again, don't overanalyze this. Double size.
Wouldn't it be the same? You just add the bits.
Yeah, you just clone it 8 times. Okay, except that in one of them I will have A0's, A1's bit number 0. The next copy will get the bit number 1, bit number 2, bit number 3 through bit number 7. S signal would be the same everywhere. S0 will feed to corresponding lines everywhere, and so on and so forth. Okay, so because remember the control is the same. For every bit I have to say, like if I want to select A1, to every bit I would say bit number 0, select A1 bit number 0. For bit number 1, I want to say select bit number 1 from A1 again. For bit number 2, same message, right? So the control signal would be common to everyone, but the data bits, the A0, A1, A2, A3 will differ in the different copies.
You know that shortcut you just showed us about where it was like actually 2 bits to 2 bits and it's actually 2 AND gates? Is that what's going on here?
Yeah, you not quite, unfortunately not. So what will happen so let's imagine I do want to create a 2-bit multiplexer out of this. Okay, so what I will do is bit number 0 can go out here, sorry, and then I will make another copy of the same hardware. And by the way, this will be called B of 0. I'll have a B of 1 out here. This I will call as A01, A11, A1, sorry, A21, and A31. But on this line, I will still have S0, S1, S2, S3. So it's not quite the same. In that particular case, they were independent bits. But here, S0 is feeding to both of them. So I'm cloning copying the circuit. Control inputs feed are common to all of them, but the data inputs are different. And this way I can create, if I want a 32-bit multiplexer, I can create a 32-bit multiplexer. Number of bits in a multiplexer depend upon how wide your data is. So like in a computer, usually you have 32-bit data or 64-bit data. So if there's a 64-bit data, like modern processors are nowadays, then the data items are 64-bit. So the multiplexers are 64-bit. How many sources they have, like in this example, they have 4 sources, depends upon how many sources you're combining the information from. So like if I have 4 different memory banks, then I need a 4:1 multiplexer, okay? But, or 4 input multiplexer. But the number of bits depends upon my data size.
Okay. For the S,
Mm-hmm.
how many bits is the S signal? It's the N number of bits, right?
As many sources as I have.
So does that mean they're different? They could be different at K and N?
Absolutely.
So how does that work for an AND gate?
how does it work for
Well,
each AND gate? Is a 2-input AND gate, right? So again, the number of bits in S is the same as number of sources I have. Number of bits in each one of the A's, A0, A1, A2, and A3, is how wide my data is. Okay. So like for example, if I have a CPU which is a 64-bit CPU and it gets data from 4 different DIMMs, DRAM banks, each DRAM bank is going to also have 64-bit data. So my data is 64-bit, but I have 4 sources. So S would be 4-bit. I'll have 4 sources, but my data size is 64-bit. So I'll have 64 copies of this circuit, each one of them controlled by the same set of S0, S1, S2, and S3, because each one of them is 4 sources, but different bits of my data are going to feed into different copies. So data width versus control, they're 2 separate things. So S is a control signal. S is steering the right data to the right place, whereas the data width is different. Normally, when we talk about in computers how many bits something has, we're normally referring to how wide my data is. Okay, it's like 64-bit computer mean that the data width, my integer or whatever stuff being stored in the memory is 64-bit or what 32-bit in the older days, and there are still computers with 16 and 8 bits also. Okay, so let's see, we still have 10 minutes to go. Now, multiplexers are humongously important. As you can imagine that this idea of like information comes from many sources and then converges into a single thing and I need to select the right one is encountered in so many places. I mean, I gave you the example of CPU. A lot of other places like, again, if you have one of those bigger PCs with chassis where you can plug in your own cards, PCI cards and stuff like that. I don't know, anyone of you have a computer like that? Big tower computers, you plug it in. Okay. Well, they used to exist and they still exist in big computer rooms and all. But in any case, there used to be a time when you could open up your computer and plug in, buy boards and plug them in. There were slots in there and all. And guess what would happen? In there, the so-called motherboard of the computer, part of its task would be that take data from any given card and steer it to the processor. So again, multiplexer, huge multiplexers. Here I have only 4 inputs. Maybe you may need multiplexers which takes a few tens of inputs and it's converging them into my CPU. So very important function. And therefore, again, being able to implement them efficiently became quite important. So I can always implement this multiplexer using these gates, but it gets very costly very soon. So we need kind of easier ways of doing it. And here, at least for electronic systems, there's a special kind of gate which can help quite a bit. And kind of the idea is the following. So if you think of a wire, remember early on in lecture 1, I talked about how zeros and ones can be represented as voltages, right? So, and we talked about kind of this middle zone where there is no value at all, okay? So usually low voltages map to the logic 0 and high voltages map to the logic 1. And nowadays, high voltage means maybe 1.5 volt or 2 volt. It used to be, there would be 3.3 volt or 5 volt, but technology has changed. Okay. So I have wires, voltages on the wire. So now let's imagine, so I have an AND gate. When it's outputting a 1, it puts out the voltage for logic 1, and when it's outputting 0, it puts out the voltage for logic 0, which is usually close to 0 voltage. Now let's say I take 2 AND gates and I tie their outputs together. Okay, so again, each AND gate is outputting either 0 volt or 1 volt, or whatever, 0 volt, let's for the sake of argument, let's say 5 volt. So 0 volt or 5 volt for logic 0 and logic 1. I take 2 AND gates, I tie their output together. Good? No good? Any ideas?
How do you tie their outputs together?
And just wire them together, right? I mean, these are 2 AND gates, I have wires coming out, I tie them together. What would happen?
Well, if you have a 0 and a 1, then it will become a 1, I guess.
Okay, so what would happen? Okay, so if I take 120 volt and tie it to ground, what happens? Ground is 0 volt, right? So I take a wire from my 110 volt line and connect it to the ground thing. What is that called? If I put one of my finger in the 110 volt line, another finger in the ground line, what will happen to me? Short, right? Current will flow through my body and okay, I'll probably not survive it. But point is, if you connect two different voltages, bad things happen because now through a wire with very little resistance in it, a high amount of current will flow, right? So circuit will burn, smoke. Okay. So I cannot tie. So if I have gates of these types which always output a voltage, either ground, whatever, 0 volt or 5 volt, and I tie them together, then bad things can happen if they're outputting different things. If they're both outputting 0, it's fine. If they're both outputting 1, it's fine. But if one outputs 0, one outputs 1, things will go bad. And in fact, even if they're both outputting 1, things can go bad if their ones are not exactly the same voltage and vice versa. So I cannot connect things with different voltages together. So I cannot tie outputs of gates just like that. But there is a special type of gate that is made which is called a tri-state gate. A tri-state gate, as the name implies, 3 states. So it can output logic 0, it can output logic 1, and it can output something which we call as high impedance or floating. High impedance, those of your E refers to resistance, is basically saying I'm disconnecting myself from the output. Okay, so tri-state basically means that it can either output 0 or output 1, or it can disconnect itself from output. And to put, so you would see that there are these gates where there is an enable signal. And what this enable signal does is, if enable is high, so this is an inverter as you can see out here. If the so this inverter, if the enable is high, it acts like a normal inverter. So if input is 0, output is going to be 1. If input is 1, output is going to be 0. But if enable is 0, then it disconnects itself from the output. Electrically disconnects. Okay, so input has no effect. And now it's very nice because what I can do is, if I have these special gates which can disconnect themselves from the output, then I can tie their outputs together and just make sure that at any given time, only one of them is actually active, right? Because the others will remain disconnected. So this is called tri-state. It's very easy to implement at the transistor level, so nothing very deep happening circuit-wise out there, but they're very useful because, as we'll shortly see, we can create multiplexers using them. This, on the right-hand side, this symbol without an invert, this is an identity module. It's something which doesn't invert. It's called a buffer. So this is called a tri-state buffer. Again, a tri-state buffer, what it does is, if enable is high, then output is exactly the same as input. But if enable is low, logic 0, then output is disconnected, electrically disconnected. Okay. If all I had was a tri-state gate like this, and I disabled it, set enable to 0, and then on the output, if I were to put oscilloscope to see what I have, I'll see nothing there. Okay, it would be just a bunch of noise because no one is putting a voltage on it. Okay, it's like a piece of wire, floating piece of wire. So you would see many different. I've written it as X out here. Sorry, I've called it disconnected out here. There are other terms which are used for kind of high impedance or floating or high Z. These are all terms that you would see referring to them. So electrically disconnected. It's also called as floating. It's also called as high Z, which stands for high impedance. Z is the term used for impedance. Okay, so these are also terms used for this thing. Okay, they all mean the same thing. Okay, it's basically saying that essentially, if no one else is driving that output, no other gate, then this gate is just floating with no connection to anything. Okay, and like I said, if you put an oscilloscope, anyone doesn't know what an oscilloscope is? You know, okay. So oscilloscope is a test instrument which electrical engineers, for the most part, like to use to monitor electrical signals. Okay, you can multimeter is probably something you may have seen at homes and all. Oscilloscopes can also give you timing waveforms and stuff like that. So they actually at least the kind of little boxes with screens, waveforms floating around and all. You might have seen pictures of them and also they are called scopes. So if I connect it, you'll see noise, like just no particular voltage because no one is driving it. Okay, so that with that digression on these tri-state gates, shoot. Okay. So why are tri-state gates useful? Because I can create multiplexers out of them very nicely. Okay. So let's say I want to create a 100:1 multiplexer. 100 sources feeding into one. What I can do is I can take 100 tri-state inverters or tri-state buffers and make sure that 99 of them are are high impedance, floating, disconnected at any given time, and the one which is a desired one is pumping on the output. In this case, I'm showing the same 4:1 multiplexer, which was a running example. So I have 4 sources, A0, A1, A2, A3. I'm using tri-state inverters, or could have been tri-state buffers. Each one of them having its own enable signal. This is my control signal, the S signal earlier on. And what will happen is I'll make sure that of these 4 enables, exactly one is high. The other 3 are 0. And therefore, 3 of these tri-state gates will be disconnected. And the one which is connected will be the one whose input will appear on the output side, inverted in this particular case. So it's literally kind of, this is kind of analogous to, I guess, mechanical relays. They're often used in like swimming pool systems and stuff like that, where like you're feeding the control to the motor from one of the inputs. Or another example, old telephone switches, they all used to operate like this, multiplexers. So in terms of truth table, what it ends up looking like is on the right hand side, if you see, I have 4 enables signals. So there are 16 possibilities. Some of them are invalid and some of them are valid. So let's go with this. Okay, so if all the enables are zeros, then no gate is driving X, so X is floating. If E3, E2, E1 are 0 and E0 is high, then only gate number 0 is driving, and therefore the output is going to be not A0, complement of A0. If I go to the next one, 0, 0, 1, 0, only gate number 1 is driving, so it's not of A1. What happens out here if 2 of them are driving? So E3 is 0, E2 is 0, E1 is high, and E0 is high. So both the top 2 gates are driving. And so what happens in the output? Well, if A0 and A1 were both high, output would be high. If A0 and A1 were both 0, output would be 0. But generally speaking, we cannot guarantee that they are the same. A0 and A1 may be 1, 0 or 0, 1. And in that case, the output would be totally bogus, some voltage which is gibberish. And therefore, we indicate that as invalid. Okay. And in fact, if the same situation happens at the same time, many places in your chip can consume a lot of current and burn or whatever can happen. Okay, usually though it's very unlikely that the situation will happen for any extended duration of time, so you don't see smoking chips and all, but still invalid signal. So what do you think will happen in the next row? Well, next row we see 0, 1, 0, 0, so that's A3, so it will be not A3. Sorry, not A2, it's line number 2. Next line, again, we see 0, 1, 0, 1. There are 2 gates which are driving the output, so that would be invalid. So that would be invalid, and I think rest of the table looks like this. Okay, so it's the job of your logic now to make sure that out of these E0, E1, E2, and E3, not more than 1 are valid at any given point in time. Okay, if they are, then the output on their at X, the voltage on X would be gibberish, and it will not make any logical sense in general. So a very elegant, nice implementation of a multiplexer is by using tri-state buffers, which are non-inverting, unlike my previous slide. So I feed A0, A1, A2, and A3 to the input of the buffers, S0, S1, S2, and S3 to the control inputs, to the enable inputs, and now I have my multiplexer. So if you have tri-state stuff, I can make very large multiplexers. By large, I mean many sources, so like 100:1 multiplexer very efficiently. All I need to do is just keep adding more of these tri-state buffers and then tie their output out here together. Okay, so they work very nicely, very elegantly, create very efficient multiplexers very nicely. So at a circuit level, that's what's done. I notice I went over time, so I'm going to stop out here. But just to summarize, we saw encoders, decoders, and multiplexers, 3 very important modules. So see you guys on Monday. And as I sent an email around, I will not hold office hours this week, but if you have questions related to homework, so Salma and Paul still will. And I'm going to be around on Saturday for some time, so I can hold an office hour if you guys ask me or something. Otherwise, on Monday, I will have office